Module 6, we're going to be looking more deeply at connections between variables, which can be described using simple linear regression or correlation. In this module, we'll first examine the concepts of correlation and linear regression. Then we'll start with a significant be the human task, setting up the regression. Third, we'll turn to how to use Excel to run a regression. Finally, we'll be the human again and discuss how to interpret the results from a simple linear regression. But first, correlation. Correlation is a way of measuring the association between two variables. Technically, it is the covariance of the two variables divided by the product of the standard deviations of the two variables. Don't worry too much about the details, just know that correlation tells you how well the two variables have a straight line sort of relationship between them. The scaling of the correlation means that it will always be between -1 and +1, with -1 meaning there is a perfect negative correlation. That is, all the points would fall on a downward sloping straight line. And +1 indicates a positive correlation that is also perfect, with all the points falling on an upward sloping straight line. A value of 0 indicates no correlation at all. This might be because there is a nonlinear relationship, perhaps a U or a V shape, or it might be there is no clear relationship at all. Here are the extreme cases. To the left, a perfect +1 correlation. To the right, a perfect -1 correlation. Notice that for each, I can draw a perfect straight line that runs through every point. The only difference is the slope of that line. However, there is an important point. Correlation is not the same thing as slope. As long as the points line up in a straight, upward sloping line, it doesn't matter how steep the line is, the correlation is 1. Put another way, a strong correlation, that is with a large magnitude, indicates that one of the variables can easily be predicted based on the other if we know the formula for the line. Put another way, a strong correlation, that is close to -1 or close to +1, indicates that one of the variables can be predicted if we know the other one. We'd have to know the equation of the line. The correlation doesn't tell us much about the line, just if it's upward or downward sloping. But it does indicate that a useful line exists. Now, most of the time, you won't find perfect straight lines. You'll have less extreme cases that nonetheless come close to having a straight line form. Here we have a correlation of +0.7 and -0.4. In both cases, we can imagine a straight line that passes near the points, even if it's not perfect. The correlations here indicate that the line does a bit better job on average for the positive relationship on the left than the negative relationship on the right, even though on the right there is one point that the line goes straight through. Finally, consider the last case of correlation, of 0. When correlation is 0, we might have a case, like on the left, where it's not obvious whether this relationship should be positive or negative. Put another way, there's no clear relationship at all. In the case where we have lots of data points, these will tend to look like a cloud, without being really clearly clustered around any particular line. Another possibility, though, is that we have a case, like on the right, where there is a clear, extremely predictable, upside-down V-shaped relationship between x and y. The problem for correlation, though, is very much like on the left. There's neither an upward nor downward sloping line that would really be right here, since the relationship changes partway through. In effect, the positive correlation in the left half of the rightmost graph is offset by the negative correlation in the right half of that graph, so that overall the correlation is 0. All to say, the lack of correlation shows that there isn't a clear linear relationship, not that there isn't a relationship at all. In terms of implementation, correlation is easy to calculate in Excel with the correl function or the correlation option in the data analysis tool. The correl function is fast, but the data analysis tool allows the selection of multiple data series and will look for correlations between every possible pair in that data series. In terms of significance, a good rule of thumb is that a correlation is considered significant if the absolute value of the correlation is more than 2 divided by the square root of your sample size. So if you have 16 observations for x and y, then you'd need a correlation of at least 0.5, that's 2 divided by the square root of 16, or 2 divided by 4, to be considered statistically significant. This isn't as rigorous as the true tests for significance, but it will typically get the job done. As a matter of interpretation, it's important to remember that correlation does not imply causation. Just because x and y are strongly correlated, we can't then conclude that x causes y. The opposite might be true. We call this reverse causation. Or perhaps there is some other factor that's causing both of the observed variables, something we call confounding. Or it might be that there isn't any causal connection at all, a case of what we call spurious correlation. TylerVigan.com documents a number of cases where there are surprisingly strong correlations, but odds are quite good that there is no causation. For example, the age of Miss America has a very strong correlation with the number of murders by steam, hot vapors, and hot objects, a correlation of almost 0.9. Yet it seems fairly obvious that there would be no causal story here. That being the case, when we find strong correlations, whether positive or negative, we should think of them as associations. Maybe they're causal, but maybe they're not. This discernment is a be the human task. But what we can say is that if there is such an association, then there will be some equation for a straight line that does a reasonably good job describing the relationship between these two variables. Now let's turn to linear regression. While correlation tells us that there is a line, linear regression is designed to give us an estimate for a best fit for that line. So we start by assuming the association between some set of variables that can be modeled in a linear form. That is, where one variable, we'll call that the dependent or the response variable, can be written as a function which includes an intercept term and a number of other terms, each of which is a slope times some independent or explanatory variable. Finally, recognizing this model isn't going to be perfect, we include an error term. The goal of regression is to find the intercept and slopes that provide the best fit for the data we have, which in turn will allow us to make predictions of our dependent variable, depending on knowing the independent variables. This slide laid out an example of multiple regression, that is, where we have multiple independent variables. In some forms of multiple regression, we even allow for nonlinear transformations of those variables. Multiple regression falls outside of our scope here. Instead, we'll focus on simple linear regression, that is, where we have a straight line and just one independent variable. So we have the more familiar form of a linear equation, an intercept, which I'm calling A here, a slope, which I'm calling B. Add to this an error term to acknowledge that our line may not perfectly describe the relationship, and we're good to go. Now we face a problem. It's not obvious how to find the real intercept A or the real slope B. We have to estimate them. For this, we need an estimation strategy. What linear regression suggests is a strategy called least squares. Specifically, we're going to select our A and B so that the sum of squared errors is minimized. The result is the best estimate we can get under certain conditions. Specifically, we assume that the independent variables are independent of each other, of the dependent variable, and of the errors, and that the errors and independent variables are from normally distributed populations. Don't worry over much about these conditions, just know that if they aren't met, some of the statistics we're going to do in the interpretation stage stop being valid. I'm not going to do the proof here, but the result is that the estimate for the slope is equal to the correlation between x and y times the standard deviation of y divided by the standard deviation of x. And A can be found by solving the linear equation, just substituting the mean of y and the mean of x into that equation. Don't worry too much about this. It's quite rare that you'd have to do these calculations by hand. I just want you to see that while the correlation is not the slope, it does have an impact on the slope, but it is affected by the relative standard deviations of x and y as well. Now that we understand that the purpose of linear regression is to estimate a best fit linear relationship between two variables, we need to think about setting it up. The first step here is a be the human step. You have to decide what variables to use and whether they should be considered the dependent or the independent variable. I'm going to assume just two variables, so you'll have one dependent and one independent. You just have to figure out which is which. Here, there are two possibilities. One is that you don't really have a clue about causation and don't really care about it. In that case, just assign one variable as dependent, the other as independent, and be done with it. However, in a business context, this is rarely the case. Instead, what you have in mind is some kind of causal story, or at least a story about prediction. In these cases, you'll want the cause to be the independent variable, also called the explanatory variable, and you'll want the effect to be the dependent variable, also called the response variable. Once you've decided which variable is the dependent and which is the independent, we're ready to use Excel to run the regression using the Data Analysis Tool Pack. Simply select Data, then the Data Analysis Tool Pack, and then Regression. This will reveal a dialog box like this one. I'm only going to focus on what we need for our purposes. First, the input Y range. Here is where your dependent variable is. Select those cells, and I would recommend including a label row at the very top of the cells you select. The input X range is where your independent variable is. Again, include a label row if you can. This makes the output much easier to interpret if you have a label at the top of that column and include that label with the data. One quick note. While we're focusing only on simple linear regression here in this example, you can use this tool for multiple regression. You just have to select multiple columns for the X range. The only condition is that they have to be adjacent to each other, so you have to arrange your spreadsheet correctly. Next, check the box for labels so that Excel knows that you have a label row. Finally, select where you want the output to go. This is really up to you. Now, a quick note about a couple of the other options we're not using. First, the option for constant is 0 that you can check. That would force the intercept of your line to be 0. Sometimes you might want to do this if you know that the constant has to be 0 for some reason, but usually we won't. For the confidence level, if you check that, first, Excel is always going to report a 95% confidence interval even if you don't check that option. So you don't need to check this if that's all you want. However, if you want confidence intervals other than for a 95% confidence level, say you want a 90% or 99% confidence level, then you can checkmark this and specify the confidence level you want. Residuals are a name for the errors that remain after you do the regression, so that's what that section would be about. If you analyze these, it can provide some insights into whether a linear regression is actually the right choice, but we'll just save that for a different course. We're also going to ignore this normal probability plot option, so leave that unchecked as well. So once you have your input Y range, input X range, labels checked, confidence level if you want one, and assigned where the output is going to go ahead and click OK. You'll end up with output that looks like this. Let me give some highlights first, then I'll go into more detail on a couple of these. First, the R-squared value. This measures the goodness of fit of the model. I'll go into more detail on this on the next slide, but for now, just know that the closer to 1, the better. Next are two areas that measure the statistical significance of the regression. First, the significance F. This reports the p-value of what we call an F-test. The F-test is designed to see if there actually is a statistically significant relationship between the independent variables and the dependent variable. The standard comparison point here is that 0.05 that we're used to, with statistical significance being indicated if that significance F is less than 0.05. So in this case, we'd say that our regression is statistically significant as a whole. Another point that measures statistical significance is the t-stat and p-value columns on the coefficient table. These have the standard interpretations for t-test statistics if you're doing hypothesis testing or p-values for hypothesis testing. Just here, the null hypothesis is that the coefficient in that row is equal to 0. So in this case, the intercept, you see, has a p-value of roughly 0.61 or so. That indicates the intercept is not statistically significantly different from 0. However, it looks like test 1's slope has a p-value of 0.005, That's definitely less than 0.05, so that indicates that the slope is statistically significantly different from 0. Now you may also notice that in this case the p-value for the slope looks like it's basically the same as the significance f p-value. This is going to be true for simple linear regression, but it won't be true for multiple regression. Briefly, in simple linear regression, we only have one independent variable. If we're not sure that it has an impact on the dependent variable, then we're not really sure that our regression has any impact on the dependent variable. Now, related to this is that confidence interval ranges for the coefficients that you see toward the right. Here, we can say with 95% confidence, the intercept is somewhere between negative 12.25 and positive 19.62 or so. It's a pretty wide range, which is consistent with us not being really sure that the intercept isn't just 0. After all, 0 is inside, well inside this confidence interval. Meanwhile, for the slope, we're 95% confident that the slope is between 0.32 and 1.32. So we're pretty sure the slope is above 0, which is reflected in that low p-value for the slope. Finally, and probably most importantly, the output gives us the equation of the best fit line in the coefficients column of that coefficients table. The value for the intercept is next to the label intercept. In our case, it's 3.68 or so, while the value for any slope coefficients would be next to the name of the x variable that they would be the slope for. So here, the slope on test 1 is estimated to be about 0.82 or so. We'll look into this a bit more here in a couple of slides. Now, a bit more into the details for R-squared. I have here the correlation graph from before, where the correlation was positive 0.7. I've added the best fit regression line, treating x as the independent variable, which is plotted on the horizontal axis, and y as the dependent variable plotted on the vertical axis. And I also include a line showing the mean level of y, which is right around 3. R-squared is based on the idea that any specific point's value on the y-axis is going to deviate from the mean, and we can break that deviation down into two parts, which I've illustrated here. Some of that difference will be explained by the regression. Some will be unexplained. In some cases, like the rightmost point on this example, the regression will actually over-explain. That is, the regression predicts more deviation from the mean than actually happens. So in that case, the value of the unexplained portion is negative. So to account for that, what we're going to do is take these pieces, we're going to square them up, and then we're going to sum that. So to be more precise, we'll take the deviations explained by the regression, we square and sum that. That is what we call the regression sum of squares. Then we do the same with the unexplained portions. We take those, we square them, and then we add those all up. That is what we call the error sum of squares. The R-squared is the regression sum of squares divided by the sum of the regression sum of squares with the error sum of squares. Put another way, R-squared is the percentage of the variance in y from its mean that we can explain using this regression. Since all of the values here in that equation are positive, the value has to be somewhere between 0 and 1. R-squared will be 0 if the regression sum of squares is 0. That is, if the regression doesn't actually help us predict deviations from the mean at all. It's going to be 1 if the regression is perfect, so that every data point falls exactly on the regression line, so that the errors, and therefore the error sum of squares, is exactly 0. Now in reality, R-squared is almost always between these two extremes. Numbers closer to 1 indicate that the regression does a better job explaining the variation in whatever our dependent variable is, but the precise interpretation of the value is going to be context dependent. So just ask yourself, how much of the variation in the dependent variable would you expect to be explained by a straight line relationship from the independent variable? Sometimes it should be almost 100%. For example, the R-squared connecting average speeds of drivers in the Daytona 500 and their lap times should be almost 1. That is, speed should almost entirely explain how long it takes to drive a lap. If we found a value of 0.5, that'd be shockingly low, as that means that differences in speed only account for half of the variation in lap times. However, in other cases, the relationship may be expected to be much weaker. For example, the connection between advertising spending and sales. Sales are affected by lots of things, not just advertising. So an R squared of 0.5 would actually be quite high. Differences in advertising spending would explain half of the difference that we see in sales. That's huge. As a general rule, the more complicated the underlying causal processes are that result in that dependent variable, the lower we'd expect our R squared to be. That is, we don't expect a simple linear regression to describe complicated processes very well. But the simpler the underlying process, the higher we would generally expect R squared to be. Let's turn to a bit more about the regression equation. In the example I have here, I'm using test 1 scores in a course to try to predict test 2 scores in that course. So we got this equation. Y, that is the test 2 score, is equal to 3.68 plus 0.82 times the test 1 score. So let's interpret each piece. First, the intercept term. This is the average value the y variable would be predicted to take if the independent variables were all 0. So here, I'd predict that those who score 0 on the first test will, on average, score 3.68 on the second test. However, in many cases, this term isn't particularly meaningful. After all, if we look at the data, we might see that no one came close to getting a 0 on the first test. However, other times it may be meaningful. For example, consider the relationship between advertising and sales again. If we had some time periods when we weren't actively advertising, then the intercept would reflect the estimated average sales in those types of time periods. Second, the slope tells us how much a 1 unit increase in the independent variable changes the value of the dependent variable. In this example, the units are points on the tests. So we know that a 1 point increase in test 1 is associated on average with a 0.82 point increase in the test 2 score. Oh, and in an advertising regression, we might find a slope of something like 2, indicating an extra $1 of advertising brings in an additional $2 in sales. It's also important to note that the slope might be negative. All that means is that as the independent variable increases, the dependent variable decreases by that amount. This would typically be true for things like the years since a loan was given and the loan's remaining balance. We can also use the entire equation here to estimate a specific value. For example, suppose I want to know, on average, how people who scored a 70 on test 1 did on test 2. In that case, I plug 70 into the equation in the test 1 spot. So I multiply it by 0.82, I add 3.68, then I find that on average, those scoring a 70 on test 1 scored around 61 or so on test 2. One thing you may notice, I've been using this phrase on average a lot. The reason for that is that regressions estimate the average relationship between the included variables, but individual observations may be far away from that relationship. Now, there are techniques to come up with what we would call a prediction interval, that is a range in which we expect a particular observation to fall. It's similar to a confidence interval, but applied to an individual observation instead of an average. Now, I'm not going to go into the details here, but I will share a couple of quick facts about these. First, prediction intervals are going to be wider the further you get from the mean value of the independent variable. The reason is pretty simple. We have lots of data on either side of the mean, so we can be more sure of what the relationship looks like around the mean. However, as we move toward the edges of our data, we get less and less certain of our predictions. A second fact, it's generally considered to be a bad idea to use regression to extrapolate outside of the range of the data of your independent variables. In effect, we don't know that the extrapolated relationship will continue to hold if our independent variables are very different from what we've already observed. So it's much better to use regression for interpolation, that is making predictions inside the range of the data we've seen, than for extrapolation, making predictions outside of that range. All to say, don't take that 61 on test 2 too literally. It's an average result that might not reflect any specific individual very well, but it is more reliable the closer to 70 the average on test score 1 is. Take a moment and note that there are two different types of significance: statistical significance and economic significance. Statistical significance is really just concerned with whether we have good evidence that a relationship is actually real. That is, that it isn't just an illusion created by the sample we happen to have. Here we can use the significance f and the p-values for the coefficients as a guide. A second type of significance is often the one that matters more. This is what we call economic or practical significance. This gets at questions like, is the model actually useful? Are the independent variables actually important in determining the value of the dependent variable? This is something that gets reflected in the r-squared and the coefficient values. Unlike with statistical significance, though, the practical economic significance requires a lot of context to really interpret it well. We've already mentioned that sometimes an r-squared of 0.5 is really low, other times it's quite high. The same goes for slope coefficients. We can't simply say that a coefficient of 5 is high or low. It very much depends what the independent and the dependent variables are. In fact, the coefficients are dependent not just on the data, but on the units of the data. If you're regressing, say, weight on height, you'll get different coefficients if you use kilograms and centimeters than if you use pounds and inches, even for exactly the same group of people. So to understand whether a coefficient is meaningfully large or not, you have to know the unit of measurements, but also the broader context. One important note, though, statistical and economic significance are separate concepts, and they can appear in any combination. Result, then, is you may find any of 4 combinations. First, you may find both economic and statistical significance. That is, you have an r-squared that's pretty high compared to what you would expect based on the context. Slope coefficients are big, again, contextually speaking, and you have an f significance under 0.05. This means we both have good evidence that there is an effect here, and also that the effect is of practical importance. Or maybe we have neither. Maybe we have a very high significance f and a very low r-squared, slope coefficients close to 0. In that case, we have weak evidence for any effect. And if there is an effect, it's probably small. We can also end up with other weirder combinations. A high r-squared and seemingly large slopes, but a high significance f suggests there is weak evidence for the effect, but the effect might be big. This generally reflects there being a very large standard error, which is most likely the case when you have a small sample. This is kind of a weird case, but it can happen. Finally, you can have effects that are statistically significant, but small. In this case, we have solid evidence the relationships do in fact exist, but it just doesn't matter much. Maybe the r-squared is much lower than you anticipated, so that this is really just a sign that other variables that are very important for predicting this dependent variable are missing, or maybe the slope is just so small in magnitude that you really can't budge that y dependent variable very much, even with big changes in your independent variable. So let's finish up with your being the human takeaways. First, in the area of correlation, remember correlation and causation are not the same thing. Spurious correlations do exist. So try to use logic to determine if causation is actually plausible in a particular case. In the area of regression, remember to set up the regression based on expected causation whenever that's possible. If the independent variable is actually the cause and the dependent is the effect, that improves the usefulness of applying regression to decision making. Also, when interpreting the regression results, be careful. Remember that the specific predictions coming out of the regression equation are for averages, not necessarily individuals, and there's a difference between statistical and economic significance. Doing so will help to ensure that your analyses are both valid and useful.